So let me recap a little bit from last time. So I'm going to go back to stuff that I've said even in the first lecture, but the main idea is the following. So we constructed two different differential graded Lie algebras. One I will call G, and it's something that looks of the following sort. Direct sum. I'm going to ignore some slight technical issues, but that's not so important. Chains on mg0n mod sigma n minus and h bar and lambda with some differential, which I will call like this, and with bracket denoted by this. So let me recap a little bit what this means. I'm taking chains on the usual MGN. The 0 is there just to remind us that I think of them as all as outputs, no inputs. But this MG0n is just the usual MGN without even a framing. So the one that everybody knows and loves. Not compactified, not framed, nothing. I'm taking the quotient by the symmetric group action. And this minus means I'm just adding powers of U inverse. And then I'm adding these formal variables h bar and lambda for good measure. And I have an operator here, which is del, which is just the usual boundary of chains. You need not be afraid of this. And this delta is something that looks like, if you give me a chain, which I will kind of schematically draw like this, maybe something like that, and I'm choosing two outputs. I'm going to choose two outputs I and j, which happen to be labeled by u to the 0. They have to be both labeled by u to the 0. Otherwise, I'm not doing anything to them. And I'm sewing in between them a tube, but with a 360-degree rotation. So you might be a bit concerned about the fact that here I don't have a framed chains, but turns out that this twist sewing operation is defined at, it's well defined at the level of unframed chains. Or if you want, you can work on the level of framed chains and take the honest operation that I just described, and then take the homotopy quotient by the circle action. This is what the delta operator is. And the bracket is very similar. I'm just sewing two outputs of two different surfaces. So I'm not doing self-sewing between two outputs, but I'm doing one output on one surface and one output on the other, and I'm doing this operation of twist sewing. So that's one DGLA constructed from chains on moduli spaces. And there's a second one, which is very similar, and it looks something like this: direct sum of sim chains, or sorry, there's no direct sum because the symmetric power already has a direct sum. Chains on the A infinity algebra, again with a minus, h bar lambda, and with an operator here, which is b plus ub plus h bar delta, and with a bracket that's very similar. And you can think of these operators, big B and delta and the bracket, as being completely the ones that are induced from the picture that I showed before, noticing that somehow delta is obtained as a composition of two things, a sewing, a twist, a circle rotation, which translates into this big B operator, and a pairing, which translates into the generalized Mukai pairing, the one that makes sense at chain level. Now, our dream would be that there should be a map from G to H, which I would call rho A, which respects the DGLA structures. But the difficulty here is that we are having here 0 inputs. If we had a topological field theory which allowed us to plug into it things with 0 inputs, then this would be our map. And then it clearly would respect the DGLA structures because on both sides they are constructed from this twist and from this pairing. And this is how we think of the twist and the pairing as the images of these objects from the field theory. Now, moreover, we know that in G, there exists a unique Maurer-Cartan element, which we called V, the string vertex. And this V is, when written in components, it looks like VGN, H bar to the G lambda to the 2G minus 2 plus N. And the only condition I put on this V is that its V03 must be something like 1/6 times the class of a point, where this point is the fundamental class of M03 mod sigma 3. And the reason for the 1/6 is exactly because we're quotienting out by sigma 3. So that's which has 6 elements. So Maurer-Cartan in this story means that del V plus H bar delta V plus 1/2 VV is 0. This is Maurer-Cartan, which is exactly what we called the quantum master equation last time. So this we know, we cannot compute explicitly this V, but this is a general theorem that there should be, that there is such a unique element. And if we had this element, we would take beta, which will be a Maurer-Cartan element in H, to be beta equals, and I have to put this in quotes, rho A of this V. This would be our desired element in the Maurer-Cartan space of this H in chains of the A infinity algebra A. So the troubles with this are two. One is that V cannot be computed explicitly so far. And secondly, that we cannot calculate rho A of V because this map rho A is not really defined. So today we're going to begin by trying to figure out a way to go around this problem. So this is my recap. Let me check to see if there's any questions about this construction that we are trying to do so far. All right, if no questions, let me continue. So the idea is we'll replace G and H by quasi-isomorphic DGLAs, which I will call G hat and H hat. And what we will have is we're going to have a diagram that looks like this. G, this is quasi-isomorphic to G hat. H, which is quasi-isomorphic to H hat. Here we will have an explicit map rho A, This will be well defined. This is well defined. In G, we have the special element, Maurer-Cartan element V. That would map to an element V hat here. We know that any DGLA map actually gives a map on Maurer-Cartan elements. And in fact, if it's a quasi-isomorphism, it gives an isomorphism on Maurer-Cartan spaces. So this one is again unique up to homotopy, just like V was. This V hat we can map to a row A of V hat here. This would be what we would call beta hat. It will live in this space. And this will be our substitute for what beta was. If there was a beta in this H, and which I put in quotes, it should be mapping to this element. Right? So all we're doing is we're taking the kind of ideal world G and H, which we unfortunately cannot compute with and we cannot map from one to the other, and replacing them by two other things that are quasi-isomorphic to them, and then we can map from one to the other, and we can calculate. So we're good. So now let me try to explain where this DGLA structures on G hat and H hat come from. So let me go back to what created the DGLA structures on G and on H. The most important things we had were a circle action, which I can think of as sewing a tube like this with a 360-degree rotation. So this is in C1 of M011 framed, if you want. So it's a one chain because it has the whole movie information of how the point rotates through 360 degrees. And it has genus 0, 1 input, 1 output. So this is what induces a circle action. Whenever I sew this particular object to an output of something, I get the circle action on that output. So I could do it either on the chains on moduli spaces, because I know how to glue these things together, or I can look at its image into action on chains of the infinity algebra, and that gives me the big B operator on Hochschild chains. The other thing that I had was a pairing, which I will put in quotes because it's not exactly a pairing when thinking about it on chains on moduli spaces. But what that came from was that came from sewing this guy, which lives in C0 of M020 framed. So 2 inputs, no outputs, and I sew that thing. Now I was sewing this to 2 outputs. These were the 2 things that we needed to describe the DGLA structure, because then the delta operator was a combination of those 2 applied to several outputs of my things. So the new idea is to notice something very simple, that we can turn an output to an input which corresponds to sewing the same thing, the same element, but to only one input, to only one output. So the picture I want you to keep in mind is if I have some kind of Riemann surface, maybe with a bunch of inputs and a bunch of outputs, I can decide for myself, so all of these are framed nicely. Let's say I have this particular output that I want to focus on. If I sew to it the tube, oops, sorry, this doesn't let me draw nicely. Let me try again. So if I saw this tube with 2 inputs, so I just sew here, but I leave this other input free, I can think of it as becoming another input to my Riemann surface. This is coming from the prop structure of Riemann surfaces. But formally what that is, it's an operator iota, which goes from chains on MGKL framed to chains on MG K+1 L-1 framed. It's an operator like this. So what it does is it turns one output to an input. I cannot do anything the other way around. I cannot turn inputs to outputs because I do not have the corresponding tube with 0 inputs, 2 outputs. But this one I do have. So now let me introduce some notation. So if V is a vector, is a DG vector space with an action of the following group, S1 to the power K plus L, semi-direct product, sigma K cross sigma L. So what I think about it in the back of my mind, I have something like a Riemann surface with K inputs and L outputs, and I can act with the circle on each one of the inputs or each one of the outputs. That's the S1 action. So I've got K plus L independent circle actions. And I can permute the inputs or I can permute the outputs, just like in a prop. I have an action like that. That's just permuting the labels. And of course, the product is not a direct product, it's a semi-direct product, because if I rotate here and then I permute, that's the same thing as rotating somewhere else. I will denote by VHS, like this, the homotopy quotient, to be just the homotopy quotient of V by this group. But what I want to emphasize is I let sigma K acts by the alternating representation. And sigma L, I let it act by the trivial representation. So maybe I'm not saying this in a very clear way. What I'm doing is I'm taking V, I'm tensoring it with the trivial with a non-trivial one-dimensional with the alternating representation on K elements, on the inputs, and then taking the invariants, the co-invariants. So I want to clarify a little bit what this means in some concrete cases. So 2 concrete examples. One is when V is chains on MGKL framed. So here I do have this action of S1 to the power K plus L, because it's a framed moduli space, so I can rotate any input or any output. And I also have an action of sigma k and sigma L. So what I get when I do V underscore HS, well, the point is that when I take the quotient by the circle action, because the circle action is free, that's exactly the same thing as getting rid of the framing. Well, that's almost like getting rid of the framing. The only part that's not completely the same, I need to get a K bracket U module. So taking homotopy quotient corresponds to just formally adding this variable U minus 1. But I add many of them. So I get chains on MGKL unframed, right? That's the quotient of the framed one by the circle action. Adjoined U1 inverse, U2 inverse, U K plus L inverse. And then I take the quotient of this by sigma K cross sigma L, where again, I'm taking the co-invariance in this funny way where I let sigma K act by the alternating representation and sigma L by the trivial representation. And that's about as much as I can explain. So somehow all the U's get identified. So there's only one U left. So an object in here, if I want to think about it, it will look like some kind of a chain on some moduli space with K plus L. So here K equals to 2, L equals to 3, has some genus maybe. It's a chain, so it might be a higher dimensional chain. And then the inputs and the outputs are labeled by powers of U. So I could have a U minus 3 here, U minus 2 here, and so on. And the important thing is that the outputs and the inputs are not labeled. So I have lost my labeling on the outputs and on the inputs. So the outputs are completely undistinguished from each other. That's the fact that the sigma L action is completely by the trivial representation. So I'm simply identifying something where I have relabeled the inputs. But somehow those marked points, which are the inputs, they are some kind of fermionic, in the sense that if somehow behind my back somebody switches 2 of the inputs, I get minus that chain. That's all I'm saying. All right, that's the alternating representation part on sigma k. So that's concrete example number 1, which we will care about. Concrete example number 2 is when V is Hom L tensor K, L tensor L, whereas before L is the Hochschild chains of A shifted by some dimension. So again, because L is the chains of an algebra, it has a circle action. Any algebra, any Hochschild chains has a circle action. So the circle action is given by the capital B operator of con. Of course, this has its own differential little b, so it's a DG vector space. And I have symmetric group actions on the inputs and on the outputs in the obvious way. And then when I take V underscore HS, turns out that it's something of the following sort. Hom exterior algebra wedge K of L plus sim L of L minus, where here L plus means L adjoined, UL formal power 2, and L minus means L adjoined U inverse. So you can see here the wedge K. This comes from the alternating representation part. It's because I have taken invariants with respect to taking. And here I see the sim L, where I've taken the trivial representation quotient. And the reason I have a L plus here and an L minus, it has to do with the fact that normally when I take any vector space, DG vector space with circle action, VHS is V minus B plus UB. This is the usual circle action quotient. And here somehow this L plus is dual. That comes from the fact that I'm dualizing L minus into an L plus. All right. So now with these notations, I can state my next theorem. So there exist DGLAs G hat, which I can write it as like this, direct sum over G K greater than or equal to 1 and L, chains on MGKL framed, take this homotopy invariance with the circle action, and with differential here is del plus H bar delta plus iota, and a certain bracket, which I will call bracket H bar. And similarly, another H hat, which is direct sum over all G K greater than or equal to 1 and L, home wedge K L plus, sim L L minus, with differential B plus U big B plus H bar delta plus iota, and the bracket is again this bracket H bar, such that three things are happening. One, G is quasi-isomorphic to G hat via a map still called iota. H is quasi-isomorphic to H hat via another map called iota. I keep calling many things iota, but it's going to be obvious from context what I mean. Three, the Maurer-Cartan equation has a unique solution in G and hence in G hat. Well, at least up to homotopy. Let's call this unique solution V. And finally, there is the TCFT, the TFT structure on A, or maybe on chains of on L, gives a well-defined map G hat to L hat to H hat. So I can take my beta hat to be, this is rho A of V hat. Sorry, the unique solution in G hat, I call it V hat, and I take beta hat to be the image. So in order to tell you what these, yes.
Andrei, I can't read, if you scroll back down, I can't read item 4. TFT structure on.
The TFT structure on, sorry, I erased a bunch of things, on L.
On L, okay.
Right. So I remind you that what the TFT structure meant, this one, was simply saying that I have maps rho A GKL, which went from chains on MGKL framed with some shift, but let me ignore that, to hom L tensor K, L tensor L. This is what whenever you gave me a cyclic infinity algebra, that the Hochschild chains of that with some shift, which is exactly what I call L, has a structure of the target of a topological TFT. For any chains on one side, I get a map on the other side. Does this make sense? Is this good? All right, so some of these statements are direct consequences of what I've done before. So we know that the Maurer, so this DGLA G is our good old DGLA G from chains. And here there was a unique solution, as I explained last time, up to homotopy. Once you fix, so I'm hiding, I'm not stating everything completely. Once you put the initial condition on what V03 is. Now, because quasi-isomorphic DGLAs have isomorphic moduli spaces of Maurer-Cartan elements mod gauge, that means that the same statement is true in G hat. So I can call this unique element in G hat, I'm going to call it V hat. So this statement is nothing but follows from statement one and the statement from before that G has a unique solution. Secondly, the fact that the topological field theory structure on L gives a well-defined map of the GLAs G hat to H hat simply comes from the fact that in the definition of G hat and H hat, I'm only allowing K greater than or equal to 1 here. So I get a map, I do get a well-defined map like this, like this rho A GKL. And then the whole construction of taking homotopy invariants was completely equivariant with respect to the circle actions and symmetric group actions. It was coming from a map of props. So I do get maps from the homotopy quotients by the circle actions from this guy to that guy. And this map intertwines all the structures that we're constructing because we're constructing all these structures from completely prop theoretic data, like sewing circles here and there and sewing cubes here and there. Whenever I do one of those in G hat, I'm doing the same exact thing in H hat. So this map gives me a map of the GLAs. The whole construction of the GLAs structure you will see is completely prop theoretic. I'm just going to sew a bunch of things here and there. So that allows me to define this, which is a Maurer-Cartan element of H hat. All right. So the one thing that I need to tell you is how do I construct the DGLA structure on G hat? Well, you will see in a minute that once I tell you what it is on G hat, there's only one choice what to do on H hat for this whole construction to map. I'm just going to simply blindly take this, everything that I do on G hat, and whenever I see something on that I'm sewing something on chains, I'm going to do the corresponding operation on homs. The only business is the circle action turns into the big B operator and the tube turns into either the Mukai pairing or the iota. All right, so to explain what are these operators? So delta is still an operator that goes from chains on MGKL framed to chains on MGKL-2 framed. And here I take HS and here I take HS. And what it does is it's exactly as before, so to, or twist so, sorry, two outputs. So sum over all choices of such outputs. So the only difference from before is that I allow myself to have some inputs, but there is nothing, the inputs are not affected in any way. They're along for the ride. This operator delta looks exactly like before. I have a chain in moduli spaces with a bunch of inputs and a bunch of outputs. The inputs are anti-symmetrized, the outputs are symmetrized. What I do is I look at all the outputs. Anyway, I'm going to completely disregard those outputs that are not labeled by u to the 0. And whenever two outputs are labeled by u to the 0, I'm going to take those two outputs and do a twist so. So put a tube with a twist between them. That's going to create a new chain. I should have said that this is a chain of degree 1 more because of the twist sewing. The HS business here just means that the inputs and outputs are labeled by powers of u, and I'm put the differential has been changed from b to b plus ub. And the inputs have been anti-symmetrized and the outputs are symmetrized. And the reason this operation makes sense on the symmetrized outputs is because I'm summing over all choices of outputs. Now, what is the iota operator? Iota is defined as before. So I'm just sewing an output to an input and summing over all the choices of outputs and inputs. So this goes from chains on MGKL framed HS to chains, it preserves chain degree, and it goes to MGK plus 1 L minus 1 framed HS. The operators b plus ub and so on, b and ub are just so they become delta, the ordinary boundary operator. I've told you what delta is. I've told you what iota is. I need to tell you what this bracket h bar is, and that's kind of the only new, really new thing. So I'm going to define, first of all, a bracket k, which is defined as twist so k outputs to k inputs again only when u powers are 0. And then do this. So let's call this of x and y, k outputs of x to k inputs of y, and then subtract the same exact thing, but of y and x. So graphically, the picture is something like this. If I've got something with, let's say, 2 inputs and 2 outputs, and something else with, let's say, 2 inputs and 3 outputs, and I want to look at the bracket 2 of this, I'm going to, first of all, sew in all possible ways 2 outputs to 2 inputs of and this can only be done in one way. And then minus all the ways in which I can sew something like this, and then, or I could sew the 2 outputs, 2 other outputs to the 2 inputs and so on. All right. And notice that here I've created an extra genus operation, because when I sewed these 2 to these 2, that has introduced an extra genus. Okay. So notice the important thing is I only saw outputs to inputs. I never saw inputs to inputs. That's a very important thing. And but I'm allowed to do k of them at the same time. And then I define the bracket h bar to be the summation over all k greater than or equal to 1 of bracket k times h bar to the k minus 1. So somehow this should be reasonable from the point of view of the genus idea. So when the h bar keeps track of the genus. So whenever I sew 1 with 1, I do not change the genus. When I sew 2 with 2, I get 1 extra genus. When I sew 3 with 3, I get 2 extra genera, and so on. A quick question. The surfaces are still allowed to be disconnected at this point. No, these are all connected surfaces. So I no longer look at, I think Sergei's question has to do with if I have a Batalin-Vilkovitsky algebra. To get a Batalin-Vilkovitsky algebra, to have a product, I would need to have disconnected surfaces. That's what would happen when I took the product of two things. But I can work on the primitive part of this commutative algebra. And only work on the connected part. So I'm happy to answer this maybe outside of, this is a technical point, but we don't need disconnected surfaces at this point. All right, so this is what the h bar bracket is, and it's a theorem. It's a combinatorial argument, not super complicated, to show that this g hat forms a DGLA. And then I've told you how to obtain h hat by just doing exactly the same operations, but on these home spaces. Now, okay, so now we know what these DGLAs are. So I want to, so the second part of the theorem is the fact that the map iota from G to G hat and iota from H to H hat are quasi-isomorphisms. So I'm not going to try to prove this. Is not extremely difficult, again, but I want to give you an example to kind of try to bring this down to earth. So, which is a much simpler construction, but because it doesn't have a circle action. But so if I let V to be an arbitrary vector space, let's say a finite, an arbitrary vector space. And I'm looking at home V tensor K to V tensor L. This carries an action of sigma K cross sigma L. And I can take the homotopy quotient of this. So if I take the homotopy quotient where the first one acts by the alternating representation and the other one acts by the trivial representation, this is isomorphic to hom wedge KV sim LV. And then I want to notice that there is a there's a long exact sequence that looks like this. Sim NV goes to hom wedge 1V sim n minus 1V goes to hom wedge 2v sim n minus 2v, and so on, and ends with hom wedge nvk. And this sequence is completely familiar to everybody. This is just the Koszul resolution. Of the degree n part, if you want, of sim v. So if you wrote the full polynomial algebra resolution, resolve the field, and then look just at the degree n part of that resolution, this is exactly what it looks like. And we know that the important thing is that it's exact. So what we have done at an intuitive level is we were looking, this is what we wanted. And what we have done is we've replaced this guy that we wanted, but we could not work with nicely. We have replaced it by this chain complex. Right? This first one, sim and v, is the stuff that appears in G or in H. It's you in G and in H, we were taking something with n outputs which have been symmetrized. So it's an element in the symmetric power of something, if you want. We don't know how to deal with that, but we can deal with things with positive numbers of inputs. And these hom wedge IV sim n minus IV are the kind of things that we replace the first ones with. All right. So the theorem that iota is a quasi-isomorphism is just a spruced up version of this Koszul resolution fact that we all know. All right. Any questions about this? If there are no questions, let me try to work out in the last 5 minutes or so an example, which I think is very useful to work out. And this was done by Costello a long time ago. So this whole idea of working with this resolution definitely goes back to him. And the paper where we discuss this is joined with him. So what I want to do is I want to do a calculation with with these chains on ribbon graphs, with these chains on moduli spaces. But I want to do it in an explicitly computable model, so using ribbon graphs. So first of all, I need to appeal to a theorem which I cannot spend more than 5 minutes stating and explaining it, but there's a huge amount of theory behind it, but which says that the moduli space, the chain complex chains on MGKL framed admits a combinatorial model involving ribbon graphs, where sewing inputs and outputs takes combinatorial formulas. So what that means is the following thing. I can write down some combinatorial gadget, which are these decorated ribbon graphs, and I will point you to a paper by Wall and Westerlund. There's only one such paper on the web, where they give the full description of what this is. So you need to learn what ribbon graphs are. You need to learn a particular model of ribbon graphs where there's all kinds of little decorations on things. But they define for such gadgets a completely concrete way, algorithmically concrete way to define the sewing operation that we were discussing until now geometrically when by talking about moduli spaces of curves. So I will do some computations in this model, and I'm perfectly happy to answer any questions later if there are people who want to understand more details about these computations. You can trace everything down to the first chapter of Wall and Westerland word for word. So here's what I'm going to do. I'm going to first look at chains on M0, 1, 2 framed. So I'm going to try to look at this, and again with this HS decoration, which means I'm taking the homotopy quotient where the inputs are anti-symmetrized. Well, there's only one input, so there's not much very interesting, and two outputs, which are symmetrized. Now, I claim that in here there is a unique ribbon graph of degree 0. So that ribbon graph will look like this. And I fear that I will lose a lot of people here, but bear with me for a minute. I will say a few words. What are ribbon graphs? Ribbon graphs are some kind of graphs where you choose a cyclic ordering of half edges at every vertex. So in my convention, there is a cyclic ordering here, which will always be the clockwise orientation. And then in this Wall-Westerland story, actually, which goes back to Kontsevich-Soibelman, every face of the ribbon graph, every connected component of the complement of it's embedded in a Riemann surface, in a topological surface, has one leaf, and this is the leaf marking the unique face. You can see that this graph is embedded in the plane. If I embed it in the sphere, if you wish, there is only one connected component of the complement. So I have, in this face, I have one leaf. This is the leaf here. Maybe let me use a different color. And I use this X to really mark the leaf. And then there are two what are called white vertices, which signify outputs. So those two green things are outputs. This leaf is an input. So I have one face, that's the one input. I have two white vertices, which for me are green now, which are the outputs. And for the outputs, you need to mark an attaching leaf, an attaching half edge. And this is what I have signified by these thickenings here. There's only one choice here. There's no choice. And the reason this is degree 0, so this is unique of degree 0. The reason for this is because the way you calculate the degree of a ribbon graph is by taking valency of black vertices minus 3, and you sum that, plus summation valency of white vertices minus 1. And I should have had powers of u everywhere, but when I have a power of u to the 0, I pretend that it's not there. All right. So when you look at this, you can do the calculation, and it's degree 0. And I urge you to think about this for 5 minutes, but with a little piece of paper, you will see that this is the only one that can be there. Of degree 0, it was genus 0, one input, two outputs. And I'm going to take the following thing, V0, 1, 2, V0 hat 1, 2. I will define it to be 1/2 of this graph. And the reason for this 1/2, I want this ribbon graph to be iota of V003, the one that I know it exists, but I cannot compute with, which was supposed to be 1/6 of the fundamental class of a point. Now the map iota turns an input into an output into an input, but it sums over all the outputs. In here, there were 3 outputs. And so when I multiply the result by 3, I get 1/2. So somehow here, there's a distinction in the V012, there's a distinction between inputs and outputs. And so while in V003, all of them are outputs and they're undistinguished. So I get a factor of 3. All right. So now I'm going to compute the following thing. I want to compute delta of V012 hat. So I claim that the result will be the following thing. And I will first write down the answer. So it's again a ribbon graph, which has been drawn in the plane. It has one input, this guy, and 0 outputs, no more white vertices. This lives in C1 of M110 framed HS. So you can check that what has happened is I took this previous ribbon graph, and what I did is I twist sewed the 2 outputs. So you remember what the delta operation was supposed to do. It was supposed to sum over all choices of outputs, which are labeled by u to the 0. In our case, there's only one such choice. Take those outputs and do a twist sew. So let me show you how the twist sew operation has happened. I can think about the original graph like this. So I can first turn this output that was here into an input. And when I do it like this, this is iota of V012 hat. So if you think about it, now I have 2 inputs, 1 output. And the degree has stayed to be 0. Then I'm going to do a circle action. So act by the circle on the second input. So I'm now like this. And what is happening is when you act by the circle action, what you're doing is you're moving the framing to the points in the face. So what has happened is this guy has been rotated to here. And then I'm going to do the ordinary sewing of the white vertex to the second face. This is the second face, the new face that I have done. So when I do that, all I'm doing is I'm taking this, I'm deleting the white vertex and I'm gluing this guy to this guy. So what I end up with is this graph that I drew, where I'm taking this edge and sewing it here. If you want to know more details, you should read Wall and Westerlund. All the details are there. It's not very difficult to follow this calculation. And the fact that I never made any choice, I started with this V012 having coefficient 1/2. The result will also have 1/2 as a coefficient. So I get 1/2 times this. I'm ignoring all kinds of questions of orientation, which introduce signs, but I'm not going to worry about it. Now I'm going to do the last question. So what is the quantum master equation that I need to solve? So when I break it down by powers of h bar and lambda, one piece of it looks like this. B plus u big B V110 hat is equal to delta of V012 hat. So I need to find, so I want to solve this V hat 110 in this concrete model. So I've calculated this right-hand side was calculated, that was completely calculated from my explicit calculation of V012 hat and the calculation of delta. So this is with 1/2. Now let's try to understand what can be in V110 hat. So V110 hat must be a chain of degree 2, because B decreases degree and big B increases degree, but U decreases degree. So this should be in chains on M110 framed HS. So remember, maybe I should have pointed this out. This one had degree 0. As you could see from the picture that I said, you add the valency of black vertices -3 plus valencies of white vertices -1. This whole result had degree 1 because delta involved a twist sewing, so that added 1 degree. And indeed, this is degree 1 because I have here a vertex of valency 4. So this adds 1 piece to the degree. And now this B plus UB operator decreases degree, so V110 must be of degree 2. So now let's think about what things of degree 2 are there. So ribbon graphs, sorry, I'm going a bit over time, but hopefully you guys can stay 2 more minutes. Of degree 2 in M110 framed. Well, there are only 2 of them, and I will ask you to do this kind of combinatorial process yourselves. One looks like this. So you can see it has a vertex of valency 5 now here, a black vertex of valency 5. So that has degree 2. And it has genus 1. You can see that you cannot draw this in the plane. You need to draw it on a torus. So again, I remind you that my convention is that all the half edges at the vertex are ordered cyclically like this. All right. There's another ribbon graph of degree 2. You might be confused where it might come from because it's harder to draw, to think about it. But what it looks like, it's like this, but where this vertex is labeled by u to the -1. All right, a u to the -1 this graph had degree 0, but a u to the -1 raises degree by 2. And I'm going to call these graphs, let's call them X and Y. Let me calculate, let me write also degree 1 graphs. I'm going to write them down quickly in order to give them names. One of them will be like this, that we have seen before. And another one looks like this. And let me call these Z and W. Now I want to calculate explicitly what B of X is. And I claim that B of X, you can do a quick calculation It's 2 times W plus Z. Up to some signs, but let me not worry about signs here. Capital B of X will be 0. Little, or maybe let me call U B of X. It does matter, even B of X is 0. And then B of Y equals to 0, and big B of Y equals to 6Z. So if you don't worry too much about the coefficients, why I get these exact coefficients, you can see where this comes from. The little b is computed by splitting a vertex into all possible ways so that I am left with at least trivalent things on both sides. When you look at this 5-valent vertex here, there are 5 ways to split it into something of size 2 and something of size 3. 2 of those, when I split the vertex, give me Z. And they come out with the same sign. This sign I'm not going to worry about. I'm telling you that this is how it works. The other 3, so those are what you get, for example, when you split like this. When you split the vertex like this, you pretend that you separate it there, you end up with W's. So when you do that split, you get W. When you do the other 3 splits, you get Z's, but 2 of them come with opposite signs, so you get only 1 copy of Z. And about the other calculation, the fact that little b of y gives 0, that simply comes from the fact that there are only trivalent vertices here, so there's nothing to split. And big B of y, being 6Z, comes from the fact that when I do B, I'm moving my framing everywhere around this face. So I could put it here, I could put it here, and so on. And there are 6 ways to do that, and they all come with the same sign. Believe this for a second, even if you don't follow all the details. So now comes the big calculation. We want the vertex V110 hat to be some combination of this X and Y. There cannot be anything else because these are the only things of degree 2 in M110. And we want it to satisfy B plus UB of V hat 110 equals to 1/2 times this ribbon graph Z. So you might think that they don't look the same, but if you, oops, sorry, times W. So you might think that they don't look the same, but if you look carefully, this ribbon graph W that I just drew here is the same exact ribbon graph that I had here. You can kind of move them around and see that they are the same. All right, so now we have a system of linear equations, which hopefully everybody knows how to solve. So this guy is 2AW plus AZ plus 6BZ must be 1/2 W, where W and Z are just ribbon graphs, so I need to just equate the coefficients on the 2 sides. So this says that 2A equals to 1/2, therefore A is 1/4. And then A plus 6B equals to 0, because I have no Z on the right-hand side. That means that B is minus 1/24. So that tells me that I have completely calculated this V110 hat as 1/4 times the first ribbon graph minus 1/24 times this other ribbon graph, which had a U inverse here. All right, and I want to tell you just why did I do this calculation. First of all, is to show you that the string vertices can be recursively calculated one by one by one. The calculations get very big very quickly, so you need a computer to do that. But I have calculated everything up to the genus 2 vertex. The other thing I wanted to show you is that this already tells you something about some Gromov-Witten invariants. This 1/24 comes from the fact that the integral of over M11 bar of one psi class, which is in Gromov-Witten theory written as the invariant tau1 with genus 1, is 1/24. Up to a sign, it's exactly this, and the sign comes from some orientation issues. The reason this 1/24 comes up is because, so I wanted to show you how these two are related. This U-1 is exactly measuring the fact that you're putting a psi class insertion. This is what I said in my very first lecture. And you're in M11, obviously, because you're in 110. You might ask, why is there no contribution from this graph? And the answer is simply what you're doing when you're trying to calculate this, you're talking about M11 bar of a point. And a point as a category comes from, the derived category of a point is just the derived category of K modules, where K is just the field. And I'm thinking about K as a cyclic A infinity algebra in the most banal way possible. All my higher multiplications are 0, only M2 is non-zero. When you discuss this particular evaluation of the row A map, at the vertex of valency n, you're going to use an Mn minus 1. So here I would need to have an M4, and there's no M4, it's 0 for the field. So really, when you're trying to evaluate integrals for target space equals a point, only the trivalent ribbon graphs matter for you, because those are the only ones that can have an M2, that only have M2s. And then the evaluation on a ribbon graph will be 1. So you're just reading off the coefficient of that ribbon graph, maybe with a sign coming from some orientation issues. So you're reading off 1/24. So when you're trying to calculate integrals of psi classes on moduli spaces, which is what the Witten conjecture is about, all you're interested in is calculating those string vertices as ribbon graphs, and then just throwing away everything that's not trivalent. But so you can do some combinatorics and, for example, calculate the integrals of psi classes on M0 bar of any n. So those I can calculate. So genus 0 invariants I can calculate and show that they match with what's known. But in general, I can't do. So for next time, my goal is to discuss splittings and how we use them in defining Gromov-Witten invariants. So far, the splitting has played no role.